The universe is woven together by an invisible spider web of staggering size. These cosmic filaments are the largest structures in existence, immense threads of dark matter that form a hidden skeleton for the cosmos. By the end of our journey, you will understand how this vast cosmic architecture dictates the fate of galaxies, including our own. We will uncover how these filaments grew from almost nothing and explore the mysterious force that builds them. What unseen hand is responsible for weaving this grand design across the emptiness of space? That searing hot soup of particles held a secret code written in quantum script. These were not mere random ripples, but the universe's own genetic instructions. For hundreds of thousands of years, however, nothing happened. The universe was still too hot and energetic for these tiny seeds to sprout. Light and matter were locked in a frantic dance, with photons relentlessly pushing particles apart, preventing any one region from gaining too much density. It was a cosmic standoff, a battle between the outward pressure of radiant energy and the quiet, patient pull of gravity. Then, a pivotal event changed everything. The universe expanded and cooled enough for atoms to finally form, a moment we call recombination. This allowed light to travel freely for the first time, a flash we now observe as the cosmic microwave background. More importantly, it untied gravity's hands. With the constant push of light now gone, gravity was free to go to work on those primordial wrinkles. It began to gently tug on the slightly denser patches, drawing in even more matter. What was once an imperceptible quantum whisper began to grow into a clear cosmic signal. This was the true beginning of the construction of the cosmic web, the moment gravity took the blueprint and started to build. Gravity is a patient artist working on a canvas of almost unimaginable scale. With the initial blueprint imprinted on the cosmos, this relentless force began a project spanning hundreds of millions of years. It started to gently pull, drawing every bit of matter toward those faint, primordial ripples. Think of a gentle slope of sand after a light rain. The water doesn't pool evenly. It finds the tiny dips and channels, flowing along them and deepening those paths with every passing drop. Gravity works in a strikingly similar way. It did not pull matter inward from all directions at once, but guided it along specific, streamlined routes. As more and more matter, both the invisible dark matter and the familiar atoms of stars and gas, flowed into these channels, their gravitational influence grew exponentially. This is the ultimate snowball effect in the vacuum of space. Each new particle added to a filament strengthens its pull, accelerating the accumulation process and stealing material from the widening gaps between them. These growing voids are the other half of the story, the empty deserts forming as the fertile rivers of matter are carved out. This gravitational collapse is the silent, persistent engine building the largest structures we know. Yet a profound question emerges from this process. The ordinary matter we see, the stuff of planets and people, simply does not account for the sheer gravitational strength needed to weave this web so quickly. Something else, something invisible, is providing the bulk of the gravitational backbone. What is this mysterious dark matter that seems to be doing all the heavy lifting for the entire universe? The universe we see is just a fraction of the story. All the glittering galaxies and swirling nebulae account for less than 20% of all the matter in the cosmos. The rest is something far more mysterious, a ghostly substance known as dark matter. This material is fundamentally different from everything we know. It does not shine, absorb, or reflect a single particle of light. It is utterly and completely invisible to every telescope ever built, operating across the entire electromagnetic spectrum. We cannot see it, but we can feel its gravitational hand guiding everything. Its presence is betrayed by the way galaxies spin far too quickly to be held together by visible matter alone, and by the way massive galaxy clusters bend the light from objects behind them, a phenomenon known as gravitational lensing. Dark matter's defining trait is how it interacts, or more accurately, how it does not. Its particles seem to ignore the electromagnetic force entirely. This means they do not experience the pressure that light and heat exert on normal particles. While regular matter is constantly being pushed and blown about by radiation, dark matter is serene and undisturbed. It can simply clump together under the quiet, persistent pull of gravity, free from the cosmic turbulence that plagues the atomic world. This is why it was able to form the first structures, collapsing into a vast, invisible skeleton long before the first star ever flickered into existence. The magnificent cosmic filaments we observe are, at their heart, rivers of this dark matter. The galaxies we can see are merely luminous leaves floating on these deep, invisible currents. The specific shape and distribution of the entire cosmic web, the great walls and the vast empty voids, are a direct map of this underlying dark matter framework. So if dark matter forms the invisible blueprint, how does the ordinary matter, the stuff of stars and planets, find its place in this grand design? Ordinary matter arrived late to a universe already shaped by an unseen architect. This luminous material, the baryonic matter of atoms, stars, and glowing gas, found its path already laid out by the deep gravitational wells of the dark matter filaments. Think of it as water finally flowing into a network of riverbeds carved long before the rain began. This gas does not simply drift, it falls. Accelerating along these cosmic superhighways, vast streams of hydrogen and helium rush toward the intersections of the web, the dense nodes where galaxy clusters will eventually shine. But this journey is not a smooth glide. As these rivers of gas converge, they collide. The sheer force of these impacts generates immense heat, turning the gas into a searing, luminous plasma. For a time, it seems this violent turbulence might prevent anything stable from forming. Yet, given enough time and the right conditions, this hot gas can radiate away its energy, cooling down and condensing into the first dense clouds. It is within these cooled pockets, nestled deep inside the dark matter framework, that the first stars ignite. This brilliant transformation is the final step in a cosmic assembly line, where invisible threads guide raw material into luminous cities of stars. We see the glorious result, the galaxies, but the filaments themselves remain shrouded in darkness. So how can we possibly prove the existence of structures we cannot see? The answer lies not in looking for the dark matter directly, but in observing its profound effects on the light we can see. We can trace the outline of the invisible by watching how it bends the light of the seen. This is the principle behind gravitational lensing, a cosmic mirage predicted by Einstein. His theory of general relativity revealed that mass warps the very fabric of space and time. A massive object like a galaxy cluster or a cosmic filament acts like a lens in space, subtly bending the path of any light that travels past it. The effect is incredibly faint for a single filament, but by studying the shapes of not one, but millions of distant galaxies, a pattern emerges. Astronomers look for tiny, systematic distortions in these galaxy shapes, slight stretches and shears that all point in the same direction. Imagine looking at a field of distant candles through the rippled glass of an old window pane. You cannot see the glass itself, but the way it twists every single flame reveals its exact contours. In the same way, the collective distortion of countless galaxies allows scientists to draw a detailed map of the invisible mass causing the warping. These maps are our most direct charts of the cosmic web, spectacularly confirming that the universe is structured along immense, winding rivers of dark matter. Yet this reveals only the gravitational backbone. What about the ordinary matter, the hot gas that we know is also flowing through these filaments? To find that, our gaze must shift to an entirely different kind of light, one that reveals the searing heat of the universe's hidden rivers. This hot gas glows with a light our eyes can never see, emitting not in the familiar spectrum of stars, but in the high-energy realm of X-rays. It reveals itself only to our most advanced space-based observatories. Instruments like the Chandra X-ray Observatory and XMM Newton act as cosmic translators, converting this invisible energy into maps of breathtaking scale. What they reveal is a universe threaded with a faint, pervasive radiance, the signature of gas heated to millions of degrees as it plummets through the dark matter channels. Astronomers call this the warm-hot intergalactic medium, or WIM, and its discovery was a monumental achievement. For decades, our accounting of the universe's normal matter did not add up. A significant portion was simply missing from all our observations. The detection of this tenuous, superheated gas finally solved the mystery, confirming that this elusive material was hiding all along within the cosmic filaments. It is the breath of the cosmic web, a whisper-thin atmosphere that fills the largest structures in existence. This completes our inventory of the cosmic threads, revealing them as a tripartite structure. An invisible skeleton of dark matter provides the gravitational muscle. A searing hot atmosphere of ordinary gas traces its form. And finally, the brilliant galaxies we see are merely the jewels strung along its length. So, with all these components in place, what is the ultimate shape of this cosmic architecture? When we pull back our perspective to the grandest possible scale, the true architecture of the cosmos comes into focus. It is not a chaotic splatter of stars, but a beautifully organized network, a cosmic web of staggering complexity and size. This universal framework is built from three distinct components. At its densest points, where multiple threads intersect, we find immense clusters containing thousands of galaxies bound together by gravity. Radiating from these hubs are the filaments themselves, the long, winding rivers of dark matter and hot gas that form the web's connective tissue. And surrounding it all are the cosmic voids, unimaginably vast deserts of near emptiness that can stretch for hundreds of millions of light years. This entire structure, from the brightest node to the darkest void, is a direct physical consequence of gravity's patient work. It is the final, evolved state of those tiny primordial ripples, amplified over billions of years into a pattern that now defines the observable universe. This pattern repeats itself, a fractal-like tapestry visible from scales of a few million light-years all the way out to the cosmic horizon. The profound consistency of this web is our greatest clue to the universe's history. But how can we be so sure that our story of its formation is correct? We test it by building universes inside our computers, sophisticated simulations which encode the known laws of physics. Start with a nearly smooth distribution of matter and then let gravity run its course for billions of virtual years. The result is always the same, a stunningly familiar cosmic web that mirrors the one we observe through our telescopes. These digital universes confirm that gravity alone is the master architect, capable of sculpting the faintest whisper of density into the largest structures in existence. One of the most ambitious digital universes ever created is known as the Millennium Simulation. This was not a simple animation, but a colossal computational experiment that traced the fate of more than 10 billion particles of dark matter. The virtual volume was staggering, a cube of simulated space measuring over 2 billion light-years on each side. The simulation began with the smooth, almost uniform conditions of the early cosmos, the same faint quantum ripples we discussed earlier. Then, with the unyielding rules of gravity programmed in, the digital clock started ticking. For weeks, a supercomputer calculated the subtle gravitational tugs between every single one of those 10 billion particles, watching as they slowly, inevitably began to dance. The result was a cosmic ballet unfolding over billions of virtual years. From that initial smoothness, an intricate architecture emerged entirely on its own. Filaments snaked their way across the void, connecting at dense nodes, while vast empty bubbles grew between them. When scientists compared this virtual cosmos to the real maps made by our telescopes, the resemblance was breathtaking. The simulation had successfully grown a universe that looked almost exactly like our own. This was a monumental validation. It demonstrated that our standard model of cosmology, with its mysterious dark matter and dark energy, was fundamentally on the right track. The simple, relentless pull of gravity was indeed enough to sculpt the entire cosmic web from almost nothing. These digital universes are now indispensable laboratories for astronomers. They allow us to run experiments we could never perform in reality, testing how galaxies form and evolve within the web's gravitational currents. Yet every simulation is built upon a foundation of initial assumptions, the starting parameters we feed into the computer. This forces us to confront a deeper mystery. What were the true, precise conditions in that first fleeting moment of cosmic genesis? The answer lies in the very first light, a fossil glow that holds the ultimate blueprint. This faint afterglow is our ultimate time capsule. Known as the cosmic microwave background, it is a snapshot of the infant universe, captured when it was a mere 380,000 years old. This radiation is not coming from one point in the sky. It permeates every cubic centimeter of space, a ghostly echo of the universe's fiery birth. When we map it with incredible precision, using instruments like the Planck satellite, we do not see a uniform sheet of light. Instead, we find a tapestry of minuscule temperature variations, patches that are just millionths of a degree warmer or cooler than their surroundings. These tiny imperfections are not random. Each slightly warmer spot marks a region where the primordial plasma was a tiny bit denser, a region where gravity had just a little more to work with. These are the very seeds from which the entire cosmic web would grow. The precise statistical pattern of these hot and cold spots is a cosmic code. By deciphering it, scientists can read the universe's vital statistics, measuring the exact amounts of dark matter and dark energy that would dictate its entire future evolution. This fossilized light is the confirmed blueprint, the starting grid for every simulation that successfully builds a digital universe. But with this blueprint in hand, a new question arises. The universe in this baby picture is remarkably smooth, a glowing fog of hot plasma. How did it go from this state of near uniformity to the intricate, structured web of galaxies and voids we see today? The universe was about to enter its most mysterious chapter, a period of profound silence known as the Dark Ages. Following that ancient flash of light, the cosmos plunged into a profound and lengthy silence. For nearly 100 million years, the universe was a place of utter darkness, a featureless sea of neutral hydrogen and helium gas. This was the cosmic Dark Ages, an era with no stars, no galaxies, and no sources of light beyond the fading afterglow of creation itself. Yet in the blackness, the great work continued unseen. Guided by their dark matter foundations, the cosmic filaments grew ever more distinct, their gravitational pull silently gathering the primordial gas into their invisible streams. It was a quiet, patient construction project of almost unimaginable scale, setting the stage for a dramatic rebirth. This prolonged night finally ended with a cosmic dawn as the first stars flickered into existence. These were not like the stars of today. They were behemoths, hundreds of times more massive than our sun, and they lived fast and furious lives. Their intense ultraviolet radiation acted like a cosmic blowtorch, flooding the universe with energetic photons that began to strip electrons from the neutral hydrogen atoms in a process called reionization. Think of a dense morning fog slowly burning away under the rising sun. Over hundreds of millions of years, these first stellar fires burned away the opaque fog that had filled the cosmos, rendering the universe transparent once more and allowing light to travel freely across vast distances. This was not a gentle transition. The energy from these first stars and galaxies did not just clear the fog, it sent powerful shock waves through the intergalactic medium. This energy heated the gas within the filaments, pushing back against gravity's pull and fundamentally changing the rules for how future galaxies would form. It dictated which pockets of gas could cool and collapse into new stars, and which would remain too hot and diffuse. Reionization was the transformative moment when the invisible cosmic web began to be decorated with points of light, the first visible signposts on the dark matter highway. This intricate interplay between the web's structure and the energy of the first stars forces a pivotal question. How does this vast, invisible architecture continue to govern the life and death of the galaxies we see around us today? A galaxy's position within the cosmic web is the single greatest factor in its destiny. Think of these filaments not as static threads, but as active galactic fuel lines, immense cosmic conveyor belts that deliver the raw hydrogen gas required to build new stars. For a galaxy nestled along one of these rivers, the supply is continuous. Vast streams of cold, pristine gas flow steadily from the intergalactic wilderness, funneled directly into the galaxy's heart by the filament's immense gravitational pull. This constant replenishment allows star formation to continue for billions of years, turning a galaxy into a vibrant, blue-hued metropolis of stellar birth. But for a galaxy stranded in the emptiness of a cosmic void, the story is tragically different. Isolated from these supply lines, it has only its own finite reservoir of gas to consume. Once that fuel is spent, star formation grinds to a halt. The galaxy's massive, hot, blue stars burn out first, leaving behind only the longer-lived, cooler, red stars. The galaxy transforms into what astronomers call a red and dead system, a fading relic whose brightest days are far behind it. This stark contrast reveals the cosmic web as the universe's ultimate circulatory system, governing the life and death of galaxies by controlling their access to the essential ingredients for creation. But how exactly does this raw, intergalactic gas complete its journey from the filament to the heart of a galaxy? The answer lies in understanding the two distinct states this material can take. For decades, a significant portion of the universe's ordinary matter was simply missing. All our observations of stars, galaxies, and gas clouds could not account for what the Big Bang theory insisted must be there. The solution to this cosmic mystery was hiding in plain sight, woven into the very fabric of the cosmic web. It is called the warm-hot intergalactic medium, or WIM, a ghostly atmosphere of gas heated to millions of degrees. This is not the dense, glowing gas of a star, but an incredibly tenuous fog that fills the cosmic filaments. Detecting it required a brilliant observational trick. Astronomers turned to the universe's most brilliant lighthouses, distant objects known as quasars. As the intense light from a quasar travels across billions of light years to reach us, it passes through these filaments. The superheated gas in the WIM doesn't emit much light, but it does absorb very specific wavelengths, leaving faint, telltale fingerprints in the quasar spectrum. It is like identifying a distant fog by the unique pattern of colors it subtracts from a powerful searchlight's beam. Each successful detection is a hard-won victory, confirming that this elusive matter was indeed shock-heated as it plummeted into the dark matter's gravitational embrace. Finding the WIM completed our cosmic inventory, accounting for the final portion of the universe's normal matter. It is the gossamer thread, the breadth of the web, making the invisible architecture tangible. But how do we move from detecting these individual components to witnessing the entire, magnificent structure in a single, unifying view? A new generation of sky surveys is turning this dream into a breathtaking reality. These galactic maps are the ultimate cosmic cartography. For decades, astronomers have been engaged in a monumental census of the heavens, using powerful telescopes to systematically chart the positions and distances of millions of galaxies. The Sloan Digital Sky Survey, one of the most ambitious of these projects, has given us a three-dimensional atlas of the local universe. When you plot all those points of light, a breathtaking pattern emerges from the noise. The galaxies are not scattered randomly. They trace out immense, winding walls and long, delicate threads, confirming the cosmic web in luminous detail. This is like seeing the first accurate map of a vast, unknown continent, revealing its mountain ranges, river valleys, and sprawling deserts. The glowing galaxies are our guideposts, allowing us to trace the outline of the invisible dark matter filaments that guide them. Now, a new generation of surveys is taking this science to a staggering new level. Instruments like the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope are mapping tens of millions of galaxies, probing the web's structure with a precision that was once unimaginable. They are measuring the subtle tug of dark matter and the repulsive push of dark energy across cosmic time. These are not just exercises in mapping for its own sake. They are fundamental tests of our entire understanding of the cosmos. The precise architecture of the cosmic web, the thickness of its filaments and the sizes of its voids, holds the key to understanding the universe's most mysterious component, the force we call dark energy. The grand cosmic architecture is not a finished sculpture, but a scene in a slow-motion battle. For billions of years, the attractive force of gravity has been the undisputed champion, tirelessly pulling matter into filaments, nodes, and walls. Its patient work gave the universe its intricate structure, yet a challenger has emerged from the vacuum of space itself, a repulsive force known as dark energy. Think of it as an anti-gravity effect, a steady pressure woven into the fabric of reality that causes the expansion of the universe to accelerate. This is not a future threat, it is happening now. As the universe grows larger and more diffuse, the influence of dark energy grows stronger, while gravity's pull over vast distances weakens. We are witnessing a cosmic tipping point. The relentless acceleration of space itself is beginning to oppose gravity's pull, potentially placing an upper limit on the size of cosmic structures. The growth of new filaments could slow to a crawl, and the flow of fresh gas into existing galaxies may one day be severed. The fate of the entire cosmic web hinges on the outcome of this struggle. By meticulously measuring the properties of the universe's most massive filaments, their thickness and how matter moves along them across cosmic time, cosmologists can take the temperature of this battle. These immense structures are the universe's most sensitive scales, weighing the strength of dark energy against the pull of gravity. The ultimate question is profound. Will the cosmic web continue to evolve and condense? Or will the accelerating expansion of space eventually stretch these grand filaments so thin that they fade into the background, leaving a universe of isolated galaxy clusters drifting apart in an ever-cooling darkness. The answer is written in the geometry of the web itself, a code we are only now learning to read, stretching across an almost incomprehensible void. The Sloan Great Wall is a leviathan of the cosmos. This colossal filament, a chain of superclusters over 1.3 billion light-years in length, redefines our very idea of a cosmic structure. Discovered within the Sloan Digital Sky Survey's vast map of the heavens, it is not a solid barrier but a sprawling, gauzy concentration of galaxies. Think of it as a continental shelf on a universal scale, a place where the density of galactic cities is simply far greater than the desolate voids on either side. It represents a superhighway within the cosmic web, a place where the underlying dark matter river runs exceptionally deep and wide. The existence of such a titanic structure pushes the very limits of our cosmological models. According to our best understanding of gravity and the universe's age, there is a theoretical maximum size for structures that should have had time to form. The Sloan Great Wall brushes uncomfortably close to that limit. Its sheer scale forces us to question whether our standard model needs refinement, or if we are simply witnessing a statistical fluke of staggering proportions, a rare knot in the tapestry that is larger than anyone predicted. This makes it a priceless natural laboratory. By studying its detailed anatomy, how galaxies move within its gravitational field, and how its mass is distributed, we can conduct a fundamental stress test on our core theories of the universe. It is a measuring stick for the power of gravity over billions of years. Yet for every record-breaking giant we find, we are left wondering if it is truly the champion, or merely the largest structure we have been able to see with our current technology. What even grander architecture lies just beyond the resolution of our telescopes, hidden in the deeper darkness? Beyond even the staggering scale of the Sloan Great Wall lies a structure so immense it strains the very definition of what is possible. The Hercules Corona Borealis Great Wall is a proposed titan, a filamentary complex that may stretch an almost incomprehensible 10 billion light-years from end to end. To grasp that scale, consider that this single structure spans a significant fraction of the entire observable universe. We cannot see it directly with optical telescopes. Instead, its ghostly outline was pieced together from a map of fleeting, catastrophic events. Astronomers used the brilliant flashes of gamma-ray bursts, the most powerful explosions since the Big Bang, as cosmic lighthouses. The density of these flashes revealed a colossal, concentrated wall of galaxies hidden in the distant cosmos. The very existence of such a behemoth is a subject of intense debate, for it poses a direct challenge to one of cosmology's foundational pillars, the cosmological principle. This principle states that, on sufficiently large scales, the universe should appear roughly the same in every direction and from every location, a homogeneous and isotropic cosmos. A structure as vast as the Hercules Corona Borealis Great Wall would be a glaring contradiction, a continent-sized feature in what should be a smooth cosmic ocean. If its existence is confirmed, it would force a profound revision of our standard model of the universe. It would mean that the grand cosmic web is not just a uniform tapestry, but possesses hierarchies and features of almost unimaginable size, structures that grew in ways our current physics cannot easily explain. This is the cutting edge of cosmic cartography, where every new discovery pushes the boundaries of our knowledge and forces us to question our most fundamental assumptions. We are left to wonder if the filaments we have mapped so far are merely the local threads of a web whose full grandeur extends into realms we are only beginning to probe. While the Millennium simulation revealed the dark matter skeleton, the cosmic story was far from complete. a new generation of virtual universes had to account for the turbulent life of ordinary matter. This is the grand ambition of the Illustris TNG project, a suite of simulations that breathe dynamic life into the cosmic web. Where its predecessors focused on gravity's pull, Illustris TNG weaves in the full complexity of astrophysics. It models the violent flow of superheated gas, the ignition of stars within dense clouds, and the cataclysmic explosions of supernova. It even tracks the growth of supermassive black holes at the hearts of galaxies. These are not passive features, they are active players. The simulation reveals a continuous feedback loop that governs galactic growth. When a supernova detonates or a black hole feasts on matter, it unleashes titanic winds of energy. These cosmic hurricanes blast through the galaxy, heating surrounding gas and violently ejecting it back into the intergalactic void. This process, known as feedback, acts as a universal thermostat, preventing galaxies from growing too large too quickly and shutting down star formation. The gas does not simply vanish, it is recycled. These enormous outflows enrich the cosmic filaments with heavy elements forged in stellar cores, seeding future generations of stars and planets. The result is a virtual cosmos that mirrors our own with stunning fidelity, a dynamic ecosystem where galaxies and their environment are in constant, energetic conversation. The web is not a static stage, but a living, breathing entity. This intricate dance forces a crucial question: how does a galaxy's specific address within this vast network determine its ultimate identity and fate? Our cosmic address profoundly shapes our galactic home. Take the majestic spiral galaxy, a swirling pinwheel of stars like our own Milky Way. This classic form is not an accident of birth, but a direct result of a quieter life along a cosmic filament. Here, away from the chaotic urban centers of galaxy clusters, a spiral galaxy can enjoy a steady, gentle rain of cold gas. This continuous fuel supply feeds star formation in its outer disk, while allowing the inner structure to maintain its elegant rotational dance. The spiral arms themselves are density waves, stellar traffic jams that persist because the galaxy is not constantly being jostled and disrupted. Its peaceful existence in the galactic suburbs allows it to preserve its delicate disk structure for billions of years. Now journey to the dense, bustling heart of a galaxy cluster where multiple filaments converge. The galaxies here live a life of constant interaction. In these crowded metropolitan centers, close encounters and dramatic mergers are commonplace. These galactic collisions are violent affairs. They effectively strip away the vast reservoirs of cold gas, the very raw material for new stars. Just as importantly, the gravitational turmoil during a merger completely scrambles the orderly orbits of stars, destroying any rotating disk structure. The result is a galaxy that is often elliptical in shape, a bloated sphere of aging stars with no discernible spiral arms. Its star-forming days are largely over, its gas supply either consumed in a final burst of creation or heated to such extremes that it can no longer collapse. This fundamental link between a galaxy's form and its location is a cornerstone of modern cosmology. It reveals that a galaxy's morphology is not merely a label, but a living record of its past experiences within the cosmic web. So where does this leave our own Milky Way, suspended in its local filament? Our galaxy's enduring spiral structure suggests a relatively peaceful history, one of steady accretion rather than violent upheaval. We reside in a calmer galactic neighborhood, a testament to the gentle currents of our local cosmic stream. This very peace, however, prompts a deeper inquiry into our ultimate fate, one that is tied to the largest movement in the universe. Our own Milky Way is adrift in a river of galaxies spanning an immensity we can barely comprehend. This is the Laniakea supercluster, our home on the grandest of scales. Its name, from the Hawaiian language, translates to immense heaven, a fitting title for a structure over 500 million light-years across. Within its boundaries, 100,000 galaxies are all guided by the same cosmic currents, flowing along an intricate system of dark matter filaments toward a single, mysterious destination. This focal point is known as the Great Attractor, a gravitational anomaly with the mass of tens of thousands of Milky Ways, pulling us and our neighboring superclusters toward it. The identification of Laniakea fundamentally changed how we define these colossal structures. Rather than just mapping where galaxies are, scientists traced how they move. They charted the peculiar velocities of galaxies, which is their motion after subtracting the uniform expansion of the universe. This revealed that galaxies are not simply drifting apart with the Hubble flow. They are also sliding, like water down a continental slope, into the gravitational valleys of the cosmic web. Laniakea is one of these basins of attraction, a watershed in space where every galaxy within its borders is flowing inward. Our position within this supercluster is a humble one. We do not reside at a central node, but along a relatively minor filament, a suburban spur on the vast galactic highway leading toward the dense Norma cluster near the Great Attractor. This cosmic geography gives us a tangible address within the void, transforming the abstract web into our local neighborhood. It raises a profound technical challenge, however. How can we possibly measure the subtle drift of galaxies against the overwhelming backdrop of the expanding universe? These subtle galactic drifts are the universe's way of revealing its hidden mass. To measure a galaxy's peculiar velocity, astronomers perform a kind of cosmic subtraction. They first calculate how fast the galaxy should be moving away from us due to the universe's overall expansion, a predictable rate known as the Hubble flow. Any motion that remains, that extra push or pull, is the peculiar velocity. It is the galaxy's true motion through space, a local current superimposed on the grand tide of cosmic expansion. By meticulously charting these deviations for thousands of galaxies, a breathtaking map of gravitational influence emerges. We see vast streams of galaxies all sliding in the same direction, like leaves caught in a gentle river current. These are not random wanderings, they are direct testimony to the pull of immense, unseen concentrations of mass, the great filaments and nodes of the cosmic web. The galaxies are tracing the gravitational landscape for us, flowing downhill into the deepest valleys of space-time. This technique has allowed scientists to literally weigh entire superclusters, confirming the staggering amount of dark matter required to generate such powerful flows. We are no longer looking at a static picture of the cosmos, but watching a slow-motion film of its evolution. This dynamic view shows a continuous cycle of cosmic drainage, where matter is steadily siphoned from the empty voids, channeled along the filamentary rivers, and finally deposited into the dense clusters at their intersections. The web is alive with this deliberate gravitational choreography, yet this entire understanding is built upon observing our local, modern universe. To truly test our models, we must ask if these same rules govern the cosmos in its youth, when the first strands of the web were just beginning to tighten. These brilliant beacons allow us to witness the web's childhood. Quasars are the universe's most powerful flashlights, the blazing cores of galaxies so distant their light has been traveling for over 12 billion years to reach our telescopes. Each one is powered by a ravenous supermassive black hole, a cosmic engine that heats infalling gas to incandescence, outshining its entire host galaxy. As this piercing beam of light journeys across the cosmos, it does not travel through a perfect vacuum. It passes through the tenuous gas that constitutes the early cosmic filaments. This gas leaves a ghostly signature not by what it emits but by what it subtracts. When the quasar's light finally arrives at our instruments, its full spectrum of colors is scarred with narrow, dark lines. Each line is a fingerprint, a specific wavelength of light that was absorbed by a particular element, like hydrogen or carbon, within a filament that the light passed through billions of years ago. It is as if we are analyzing a single ray of sunlight that has filtered through a distant forest, and by studying the precise patterns of shadow, we can deduce the type and density of the leaves it passed through. This absorption line technique reveals a cosmic web in its adolescence. The filaments of the young universe were more ethereal and delicate than the thick, massive structures we see today. They were still gathering their dark matter backbone, their rivers of gas not yet fully formed. This is a direct view of the construction site, a snapshot of the universe caught in the act of building its largest features. But to push our vision further back, to a time when the first filaments were just condensing from the primordial fog, we need telescopes of unprecedented power. A new eye has opened in the depths of space. The James Webb Space Telescope is not merely another observatory, it is a time machine tuned to the universe's infancy. Its powerful infrared gaze cuts through cosmic dust and stretches across billions of years, allowing it to witness the very epoch when the first strands of the cosmic web began to glow. Where the Hubble Space Telescope showed us mature galactic cities, Webb reveals the frontier settlements, the faint, young galaxies that were just starting to light up along the primordial dark matter filaments. We are no longer looking at a finished tapestry, we are watching the threads be woven in real time across cosmic history. This allows us to perform a direct test of one of cosmology's core ideas, hierarchical structure formation. Did the universe really build from the bottom up, with small structures merging into larger ones? Webb's deep field images provide the answer. They show these infant galaxies are not scattered randomly. They are already arranged in faint filamentary chains, exactly as predicted by our models of dark matter's gravitational influence. The blueprint was indeed there from the start, and Webb is watching the construction crew arrive on site. But its vision goes beyond mere mapping. By analyzing the light from these first galaxies, astronomers can discern how they are interacting with their surroundings. The intense radiation from the earliest stars would have blown powerful winds, heating the gas within their host filaments and potentially regulating the growth of neighboring galaxies. Webb's spectrographs can detect the signatures of this feedback, revealing how the first stellar fires began to clear the cosmic fog and shape the environment for all that followed. This telescope is showing us the cosmic web not as a static sculpture, but as a dynamic, living system from its very first moments. Yet to comprehend the web's full modern architecture, from our local supercluster to the Great Walls, we must chart volumes of space so vast they defy comprehension. This is the grand ambition driving a new generation of ground-based observatories. This new eye on the sky will capture the universe in motion, the Vera C. Rubin Observatory, poised to begin its monumental legacy survey of space and time, is not designed to simply take a single, static portrait of the cosmos. Its mission is to create a decade-long time-lapse movie of the heavens. Imagine a camera that photographs the entire available sky every few nights, not just once, but over and over again for 10 years. This relentless observation will detect billions of galaxies, far beyond any previous census, weaving together the most detailed and comprehensive chart of the cosmic web humanity has ever seen. But this map will be more than just a list of locations. By meticulously measuring the subtle, twisted shapes of these distant galaxies, the survey will employ weak gravitational lensing on an industrial scale. Each tiny distortion is a clue, and with billions of clues, scientists can trace the invisible dark matter filaments with a precision that was once a distant dream, mapping their ghostly geography across an unprecedented volume of the universe. This immense statistical power is key to solving the greatest cosmic puzzles. The survey will uncover rare, colossal structures, the true titans of the web, testing whether our current models of gravity and cosmic evolution can explain such behemoths. It will rigorously probe the nature of dark energy by observing how the web's structure has stretched and evolved over billions of years. To complete this dynamic picture, the Rubin Observatory's breathtaking visual survey will be complemented by other missions that provide the third dimension. Spectroscopic instruments will follow up to measure precise distances to millions of these galaxies, transforming the vast two-dimensional map into a rich, three-dimensional atlas, revealing the cosmic web not as a frozen sculpture, but as a living, breathing entity whose grand story is still unfolding. A redshift is the universe's fingerprint, a unique signature that reveals not just where a galaxy is, but how it moves through the expanding cosmos, while imaging surveys like the one planned for the Vera C. Rubin Observatory provide a stunning two-dimensional map of the sky. It is the spectroscopic surveys that add the crucial third dimension of depth. Instruments like the Dark Energy Spectroscopic Instrument and the upcoming 4-meter multi-object spectroscopic telescope project are built for this exact purpose. They do not merely photograph galaxies, they dissect their light. By precisely measuring the redshift of millions of celestial objects, these projects can calculate their exact distances from us. This transforms a flat image into a rich, three-dimensional model, allowing us to see the cosmic filaments not as smeared lines on a photograph, but as true, winding rivers of matter with vast, empty chasms between them. The resulting maps are the most detailed charts of the cosmic web ever produced, revealing its intricate branching patterns and the subtle ways different types of galaxies sort themselves within this vast architecture. Some filaments are rich with vibrant, star-forming spirals, while others are lined with older, redder galaxies, telling a story of the environment's influence over billions of years. But the data reveals more than just structure, it reveals motion. By comparing the redshifts of galaxies within a single filament, astronomers can detect cosmic flows, the slow, river-like movement of entire galaxies sliding along these dark matter channels toward the dense clusters at their intersections. This provides a dynamic view of the web in action, showing us how it actively shepherds and shapes the galaxies within its grasp. This powerful combination of imaging, spectroscopy, and supercomputer simulation is weaving together a complete picture of a cosmic ecosystem, a living network where every component interacts. Yet to fully understand this ecosystem, we must turn our gaze away from the bright nodes and dense filaments and into the profound emptiness of the voids. These immense cosmic deserts hold a profound silence. While the filaments gather matter into brilliant cities of light, the voids are the expanding countryside, the vast and ever-growing emptiness that makes up most of the universe's volume. They are not perfect vacuums, but are instead sparsely populated with a few isolated dwarf galaxies and a whisper-thin mist of hydrogen gas. These voids are defined by what surrounds them, their boundaries traced by the bright walls and filaments of the cosmic web. Think of the universe as a rising loaf of raisin bread. The raisins represent galaxies and clusters, while the dough is the void space. As the bread expands, the raisins move further apart, but the empty spaces between them grow even faster. This is the essence of void evolution. Gravity is the great real estate agent of the cosmos, relentlessly pulling matter out of these quiet regions and into the bustling galactic metropolises. With every passing eon, the voids become larger, darker, and more empty. This relentless evacuation makes them a remarkably clean laboratory for testing the fundamental laws of the cosmos. Unlike the violent, complex environments within galaxy clusters, voids are serene. The physics here is dominated by the pure, smooth pull of gravity and the subtle push of dark energy, uncomplicated by supernova or black hole feedback. By measuring the rate at which these voids expand, scientists can take the most direct measurement of dark energy strength, observing how this mysterious force accelerates the emptying of the cosmos. The true nature of the universe is written in the geometry of both the full and the empty. The specific way the dense filaments and empty voids connect, creating a vast cosmic sponge, leaves a unique statistical signature on the distribution of all matter. This large-scale topology is a fundamental prediction of our cosmological models, and by charting the voids, we are checking the universe's most basic blueprint. This cosmic sponge is a precise geometric signature of the universe's birth. The topology of the cosmic web, its sponge-like nature, means that the full and the empty are equally fundamental and interconnected. You cannot have a vast, continuous void without it being entirely surrounded by a single, unbroken membrane of denser material, and you cannot have a long, winding filament without it bordering empty space on all sides. This specific arrangement of clusters, tunnels, and bubbles is a direct prediction of our standard model of cosmology. To quantify this shape, mathematicians use sophisticated tools that measure its essential character. One such measure is called the genus, which essentially counts the number of handles or tunnels in the cosmic structure, much like you would count the holes in a complex sponge. A high genus number means a highly interconnected universe, full of passages and voids. When scientists apply these measures to the real distribution of galaxies from immense sky surveys, and then compare that to the virtual universes generated by supercomputers, the match is remarkable. This geometric agreement is a profound confirmation. It tells us that the initial seeds of all structure, those tiny quantum ripples in the early universe, must have been a specific kind of random, known as Gaussian fluctuations. It was from this particular statistical blueprint that gravity could sculpt the single, continuous network we observe today. This topological test is powerful because it is independent of other methods, relying purely on the geometry of the large-scale structure itself. It confirms that our core story of cosmic evolution is fundamentally correct. Yet such a clean, mathematical result also invites a deeper question. Does this beautiful agreement mean our model is complete, or could the subtle details of the cosmic web's geometry eventually reveal cracks in our understanding, pointing toward new physics hidden within the universe's largest pattern? The cosmic web is a proving ground for the laws of physics themselves. While Einstein's theory of general relativity has masterfully predicted everything from black holes to gravitational waves, it relies on a mysterious, invisible component to explain the universe's structure, dark matter. Some scientists have proposed a radical alternative. What if our understanding of gravity is simply incomplete? Could a modified theory of gravity explain the motions of galaxies and the web's architecture without needing any dark matter at all? One prominent idea, known as modified Newtonian dynamics or MUND, suggests that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies. This can indeed explain how individual galaxies rotate, but when confronted with the grand scale of the cosmic web, these alternative theories often struggle. They have a difficult time reproducing the specific, intricate patterns we observe, the precise thickness of the filaments, the staggering sizes of the voids, and the immense mass of galaxy clusters. The relentless way gravity pulls matter into streams and nodes over billions of years creates a signature that is incredibly difficult to mimic. The standard model of cosmology, with its dark matter backbone, successfully grew these structures in supercomputer simulations starting from the primordial blueprint. The fact that its predictions so closely match our observations of the real cosmic web is one of the most compelling reasons to believe that dark matter is real. This vast network is more than a spectacle. It is a stringent test, a cosmic laboratory where we can probe the fundamental rules that govern the universe on the largest scales imaginable. As our maps of this web grow ever more precise, they may even allow us to study the properties of the dark matter particle itself, understanding not just its gravitational effect, but its true nature. These immense filaments are the ultimate dark matter laboratories. While we have mapped their gravitational shadow, the true identity of the particles that form them remains physics' most profound enigma. Every filament is a colossal reservoir of this unknown substance, a vast river of particles that have never been directly seen. The key to unlocking their secret may lie not in isolating a single particle, but in observing how they collectively shape their own environment. If dark matter particles can interact with each other, even in the most minuscule way, or decay over cosmic timescales, it would leave a subtle fingerprint on the architecture of the web itself. For example, our standard model assumes cold dark matter, particles that move slowly and clump together efficiently, creating dense filament cores, but some theories propose a warmer version. In this scenario, faster-moving particles would resist being packed too tightly, leading to filaments that are slightly more diffuse with less concentrated cores. This is a difference a telescope could never see directly, but a gravitational lensing survey mapping the density of these structures with exquisite precision might be able to detect it. The faint variations in how matter is distributed within a filament could be the clue that distinguishes one theoretical particle from another. This transforms the entire cosmic web from a magnificent structure into a fundamental scientific instrument. It connects the vast billion light-year scales of the universe directly to the realm of subatomic physics, allowing us to use the largest structures in existence to probe the smallest. This grand pursuit to understand the invisible fabric of reality inevitably leads us to reflect on our own tiny place within this immense, evolving tapestry. Our existence is intertwined with the architecture of the cosmos itself. This leads to a profound and deeply philosophical question, one that connects the vast cosmic web directly to our own presence here. Some thinkers propose that the specific physical constants of our universe, including the exact strength of those initial quantum ripples, appear finely tuned. Had those primordial wrinkles been even slightly weaker, gravity's pull would have been too feeble to gather matter into galaxies and stars. Conversely, had they been stronger, matter would have collapsed into a chaotic storm of giant black holes, a universe far too violent for stable planetary systems to ever emerge. The cosmic web, with its specific texture and scale, represents a golden mean. It provides just the right environment for galaxies to form and evolve at a sustainable pace, allowing for the long, quiet periods necessary for complex chemistry and ultimately life to arise. Finding our Milky Way situated on a gentle filament within the Laniakea supercluster is not a random accident of address. It may be a necessary condition for a world like ours to exist. This line of reasoning, known as the anthropic principle, is deeply speculative, yet it frames the cosmic web in an entirely new light. These filaments are more than a celestial spectacle. They are a fundamental part of a chain of events stretching from the first fleeting moment of time to the conscious minds now contemplating their origin. Our journey from those quantum seeds to this vast, invisible network reveals a universe capable of building complexity on the grandest scales. A universe that is not only observable, but in at least one quiet corner, deeply known. From the faintest quantum whispers to the largest structures in existence, this cosmic tapestry is the ultimate expression of natural law. We have traced the journey from an invisible dark matter skeleton to the brilliant galaxies that light its pathways, all woven together by the patient, relentless hand of gravity. Our tools have evolved from simple telescopes to vast digital simulations and sky-spanning surveys, each confirming a universe that is deeply interconnected and dynamically evolving. These filaments are not merely features in the cosmos, they are its fundamental architecture, the framework upon which galaxies are built, and the very platforms that make life possible. As our vision extends further with ever more powerful observatories and computers, the next chapter of this great story awaits. The once invisible web is slowly coming into focus, a breathtaking reminder of the profound beauty and intricate complexity of our universe. Thank you for sharing this journey across the largest scales of space and time.